So we've laid the groundwork to do some pretty neat things with a lot of in the first 5 chapters, and now we're going to look into some neat things like the line of best fit and how is that related to vectors? How is that related to matrices? Um, how do you get the best answer from the data that you have? And that's what a line of best fit is. And then we have something called a Fourier approximation, which is some more advanced math that you could use later on. So we're going to look at the length and orthogonal stuff, orthogonal vectors, and how they're related to other things that we can do, not just with matrices. So the inner product is really just the dot product and what we've done before. But technically, if they're in matrices, vectors are kind of the same thing. But if I want to get out a number, this is really important that when we're doing this, that when we're doing a dot product, we always get out a number, not a vector. And that's kind of been our bugaboo like throughout the whole year, really. Knowing when the question is asking for whether or not the answer is going to be a number or whether or not the answer is going to be a vector. So, and we can do them just like we did normally. You can change these column vectors to vectors that you do in physics or you did in calculus. And we're just going to take the first one, transpose it so that it actually can be. This is obviously going to be a 1 by n vector, and this is going to be an n by 1 vector. And so what we're going to get out is really just a 1 by 1 or just a number. And we don't need the matrix notation anymore. So we're just going to take each of those components and really multiply across and add. That's really all that it is. So if I do v dot w, excuse me, that's going to be, so a, we'll just squeeze that right here, is going to be -1 times 4 plus 0 times 3 plus 2 times 0 plus 5 times 6. And so obviously the only thing that we have is 5 times 6 and -1 times 4, and that gives us 24. So, and then we do v minus w. So v minus w is not a dot product. We can just subtract them because they are the same dimensions. So v minus w, just change colors on that one. V minus w is going to be -5, +3, 2, -1. And if I take this green vector and I take the dot product of that, that is going to give me -10 -3 plus 6 -2. And that is going to give me -9. Okay? That's really all there is to that. So that's going to be -9. This notation right here, this is saying, all right, what is the magnitude of that vector? It's not an absolute value because it's not one number, it's the whole series of numbers. So what is the magnitude of that vector? And so if I just had 2 components, the magnitude of 2 -1 is obviously going to be the square root of 5. Just take each of those components and square them. So it's going to give you the square root of 4 plus 1 plus 9 plus 4. And that is obviously the square root of 18. Simplify it if you want to, but I do not want that. I don't need that. So the square root of 18 is perfect. Now we want to find a unit vector in the direction of w. So we've been doing that before when I said, all right, fine, give me an eigenvector. And then when we simplified it, blah, 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 we got something that looked like 1/2 and 1, right? And so we said, oh, I don't want to deal with those fractions, so I'm going to change that to 1, 2. They're in the same direction. And then it wouldn't be in the same direction if I made them both negative, because then they'd be going in the opposite direction. So we're going to keep those signs. So to find the unit vector in the direction of w, we're going to keep all those numbers, 4, -3, 0, 6. So that is obviously not a unit vector. A unit vector just as one has a length of 1. So just like we saw before, on the unit circle, right? So we have a vector that's going out here, but we'll just say that's You know, the sine, you want to find the sine of pi over 4. Well, we want to lop that off, and that would be that vector. All these vectors have a radius of 1. So now we want this to be, where are we going to lop that off? We'll just say that's our 4, negative 3, 0, 6. Well, what's the magnitude of it? Well, we got to find the magnitude of W first, which is obviously going to be, 16 plus 9 plus 36, which is 61. So I could write the square root of 61 underneath all of them, or I can just be lazy and just write it once. So I'm just going to do 1 over the square root of 61. And then that is going to be a unit vector. And I could check that if I really wanted to. It's going to be 16 over 61, squaring that, plus 9 over 61, plus 0 over 61, plus 36 over 61. All I did is I took each of those components, distributed them in, and we get 61 over 61. And that's going to be our magnitude. And yep. So that's what we get on that one. So that is 1. So we have a unit vector in the direction of W. Okay? And that does need to be the square root of all those things squared. All right. So that is it for the first example. Easy enough. So if I have u and v, if those are vectors, and c is any scalar, then we have all these properties. It doesn't matter which one you did first. U dotted with v is the same as v dotted with u, because all we're doing is multiplying and adding them. So we can change those orders. We can add the two vectors first and then find the dot product, or I could have done this on the other problem. U dotted with w plus v dotted with w. And we can always pull out constants. That always works in math, and only in math, remember that. So if the dot product is always going to be positive, the dot product of the same vectors, if we have the same vector, it's always going to be positive or 0. But if it is 0, that's the only time it's going to work is if you just already had the 0 vector. Very rarely we're going to be dealing with the 0 vector. So the length of a vector is what we've already done. Now I just told you how to do what we just did. So technically you could write out another, copy that v right there, and then square it and square root and add them all together. So the magnitude of v is going to be, that needs to be the square root of v times v, v dotted with v. I think that's what yes. So magnitude squared is going to be v dot v, but not, yeah. So if we have that, we have a squared plus b squared. It's the same thing that I've already done before. And we can pull out constants. If that c is a constant, now we do need an absolute value right here. So this is looking at the difference between the absolute value, because it's just a number. It doesn't need a special absolute value around it. If we have a double absolute value around it, and then we're talking about the length of a vector, the magnitude of it. So how do you find the distance between two vectors? Well, that is just going to be, you're going to subtract the 2 and then find the magnitude. This agrees with the usual formulas. So think of it like points. So if I had these 2 points, x1 and x2, like we did in algebra, x1 and y1, excuse me, and then that would be x2 and y2, right? So what we did is we took these 2 components, x1 and x2, now we call them u1 and v1, subtracted those 2, squared them, and took the other 2 components, took the square root, squared those, square root of those. Just all it is a distance formula. And so you can think about vectors sometimes just like points. So to find the distance between those 2 things, and we just do that in our head. What is our change from positive 1 to negative 2? Well, that's going to be 3. And we're doing distance, so I can think about it just like 3. I don't have to have negative 3 squared because then I'm going to mess up. And then that distance is 2. Between those 2 components is 2. Between those 2 components is 3. between those two components is 0, and then the last one is 3. So what does that give you? Well, that gives you 9 times 3 is 27. 27 and 4 is 31. So the distance between those two vectors is going to be the square root of 31. So it's like the distance between the x's, distance between the y's, z's, a's, and b's, just going back around the alphabet. So what are orthogonal vectors? Well, you know what orthogonal vectors are. Those are two vectors that are perpendicular to each other. Just a fancy name for perpendicular. So geometrically perpendicular, if and only if those two vectors are going to be perpendicular. Here is v, and here is u. If and only if from u to v is the same distance as u to negative v. So the square of the distances are the same. Those two hypotenuses are the same. U plus v and u minus v. So I'm really not going to go, but the distance squared is kind of like our c squared. The distance between u and v. It's going to be a squared plus v squared minus 2uv. So that is going, and if I did the negative, it would come out and be those magnitude squared plus 2uv. And just looking at that real quickly to find this, let's just talk about what the heck they did right here. The distance between u and v, it's going to be u minus v squared, which is u minus v dotted with u minus v. And then when I distribute that in, I have u times u minus v plus negative v times u minus v. So it's kind of like our FOIL. We are going to take that to each of, u distributes to u and to negative v. And then negative v distributes to u and negative v. So u dot u and u dot v. So it's kind of like FOIL. This is kind of like our first terms, outer terms, inner terms, and our last terms, just like we had in Algebra 1. And so that is going to be u squared plus v squared minus 2uv. So the distance squared is going to be the magnitude squared, plus magnitude squared, and this becomes minus 2uv. And if I did the negative, I would get the exact same thing. Except that would be positive, right? Because we would have a negative v in that case. So if we have u and v are said to be orthogonal, and this is what I'm going to use most of the time. Just do the dot product. Does a dot product give us 0? And that's going to be an important check we're going to use again and again and again. They're also going to be orthogonal if we have, I was getting ahead of myself when I was thinking about this because this is the important part. C squared is equal to a squared, I need squared right there, plus b squared. So if those are legs, then that will be the only way we can get the hypotenuse, right? So, determine whether or not those two vectors are orthogonal. So just like we did before, like we saw that as -1, +3. I like vectors with that square, with the angle bracket on it, not the open bracket. So are those two vectors orthogonal? Well, what's the dot product going to be? Now, so I'll show you to you. This is kind of like the old way. We would have -4, and this is fine, +6 minus 2. That gives you 0. It's perfect. And we could also do, well, that means that this can be a leg, that can be a leg, and then u minus v is going to be a leg. So what is the magnitude of u? I'm just going to change this. The new way that we can do it is so this is going to be the square root of 9, that's going to be 14. That's u, that's the magnitude of u. The magnitude of v is 1621, right? And then u minus v. That is going to be the vector -5, 1, and 3. So what is the magnitude of that? The magnitude of u minus v is going to be the square root of 35. And now we see that that has to be, the hypotenuse has to be the largest side. The square root of 35 squared is equal to the square root of 14 squared plus the square root of 21 squared. So therefore, that answer is yes, 2 different ways. Are those 2 vectors orthogonal? Yeah, they are. Okay, because the dot product is 0. What about this one right here? Are they going to be orthogonal? So if I take the dot product, that's going to be 0 plus 6 plus 2 plus 0. That answer is no. So it's the same thing that everyone did a great job on before on prior test. Now we have orthogonal complements. So this z is going to be, it's going to come back to us in other things, so we make sure we understand that. If we have a vector that is orthogonal to every vector in the subspace of W, if every vector in the subspace W of Rn, then Z is going to be orthogonal to W. So one vector is going to be orthogonal to everything. So we did that with the cross product before. The set of the vectors Z that are orthogonal to W is called the orthogonal complement of W. We read as W perp. Okay, so all those vectors are going to be perpendicular to all the vectors that we're going to have. So we're going to have a couple of theorems on this. So we're going to see what we have for row of A. So this is saying that whatever you have in the row of A is going to be perpendicular to the null of A. And then the basis for the column of A is going to be perpendicular to the null of A transpose. So the orthogonal complement of the row space of A is the null space of A. And the orthogonal complement, the perpendicular vector or vectors, the basis, is going to be the orthogonal complement of that column space of A is the null space of A transpose. Let's look at a couple of examples with that. So let us look at that. So find a basis for the null of A. So to find the basis for the null of A, we're just going to, let's say, tell me all the vectors that give me out an answer of 0. So we can see that this thing row reduces real quickly. We still have this x1, x2, and x3, right? Because we're slow and we need to write that out. So that is going to row reduce. Those 2 rows are dependent. So that's just going to become 1, 0, negative 1, 0, 0, 0, 0, 1, 2, 3, and then we put another one in there. So again, that's saying that my basis still has 3 variables in it. So we're going to have that x1 is equal to x3, x2 is equal to 0, x2 is going to be free, and then x3 is going to equal to x3. x1 is the same as x3, so we're going to write that as a basis of, in terms of x2, which is 1, 0, 1, and x3, which is 0. Sorry, I actually did x3. Now I'll do x2. My bad. So this is in terms of x2. That's in terms of x3. So that's the basis for the null of A. What is that? Well, those 2 vectors, does that form a line or does that form a plane? Well, they're going in 2 different directions, so it's going to form a plane. And we're using all 3 of our directions, right? We're using x, we're using y, and we're using z, if you want to think about it like that. So the basis for the row of A is, to find the basis for the row of A, remember we're just going to look up here, and we only had 1 pivot, and we can use this column right here. And so the basis for the row of A, when we're going to write that first row, is 1, 0, negative 1. And if you think about that as, oops, and you can write that as just that one vector, 1, 0, -1. Well, what is that? Well, it's only going in one direction, so it's just a line, and that is in R3. It has 3 components. Now let's go back to what this said right here. The row of A is perpendicular to the null of A. So, and we can see that if I take the row of A, which is this red vector, that is going to be perpendicular to null of A. So if I take the dot product of this vector 1, and I would take the dot product of that one, I have 1 plus 0 minus 1. That has a dot product of 0, and so does this. 1 times 0, 0 plus 0 plus 0 is obviously 0. And they're in the same, they both span R3. One's a plane, one's a line. Now let's look at the basis for the column of A. Column of A, it is, now we're going to look at the only pivot that we have. That's our only pivot at 1. And we're going to write that column that we have. And that is just the vector 1, -2. What is that vector? That vector is just a line going in 2 directions. And that lies in R2. So that is a line in R2. And it's just this vector 1, -2. That's for the column of A. The null of A transpose, so we got to do A transpose first. So if I just take A and I transpose it, I have 1, 0, whoops, what is happening? 1, 0, -1, and then we have -2, 0, +2, I think. Yep. So the second row became the second column. And I want to find the null space of that. Augment that with 0, we can obviously see that that just goes away. And it's already Jesus for us, right? We have 1. So we have x1 and we have x2. And that's those are now we only have 2 variables now. And we just have 1, -2 equals 0. So x1, our vector, x is equal to, x1 is equal to 2x2, x2 is equal to x2. So we have this vector right here. And the null of A transpose only consists of this one vector going in 2 directions. So it's just going to be a line. And it could have 5 components on there, but it still would be just one thing, right? Whenever I have one thing, it's going to be a line. So 2, 1. So what do we notice about that? Geometrically, this is what the next thing is kind of showing you. The dot product is going to be 0. 2 minus 2 is 0. So we had the null of A consisted of 2 vectors. I don't know, one was 1, 0, 1, the other was 0, 1, 0. I don't care which one is which. And that is going to be our plane. And there's our line, and it goes through, and it is perpendicular to it. It is orthogonal to it. And I think that they were off a little bit. The column of A, that really should be the vector 1, -2. So if I go to 1, -2, that should be the column of A. And then the null of A is, we'll do that in green, should be 2, 1. That's the null of A transpose. So ignore the black lines, but it's kind of the same thing. They're trying to show you that they're perpendicular, they're orthogonal, and those 2 lines are, orthogonal. We'll assume that line was supposed to be, that vector was supposed to be going in that other direction. And they do just lie in R2. And that's it for 5-1 or 6-1.